Hey everyone, welcome to this explainer. Look, today we're doing something a little bit different. We are going to stop blindly memorizing physics formulas and instead start truly understanding the underlying visual geometry of our experimental instruments. Specifically, we're taking a magnifying glass to the Vernier caliper, focusing heavily on least count calculations, main scale readings, Vernier scale readings, and zero error corrections. By the end of this, you're going to be able to confidently tackle even the trickiest exam questions. Let's get right into it.
Here's our quick agenda for today. 1. Instrument anatomy. 2. Least count logic. 3. Zero error correction. 4. When formulas fail. And 5. IIT JEE PYQs.
All right, Section 1. Instrument anatomy. Beyond the main scale.
So what's truly fascinating about this instrument is just how versatile it is. You've got a fixed main scale, right, which just functions like your regular everyday ruler. But then you have this movable Vernier scale that slides right along it. And depending on what exactly you're trying to measure, you've got specific tools right there on the device. The lower jaws are used for measuring external dimensions, like the width of a block. The upper jaws are perfect for grasping internal diameters, like the inside of a pipe. And there's even a little tail or depth probe sticking out the back for measuring how deep a cylinder goes.
Moving right along to Section 2, least count logic, the smallest measurement.
Okay, here is the absolute core logic you need to grasp. Instead of just memorizing some equation from a textbook, I want you to understand that the least count is literally the tiny physical gap between a main scale mark and a Vernier scale mark when you slide it. Seriously, if you picture the physical jaws, this little gap is the absolute narrowest space you can confidently measure.
Let's think about the math and see how this actually builds. In a standard, perfectly calibrated setup, you'll see that 10 Vernier divisions fit perfectly into 9 main scale divisions. If one main scale division is 0.1 centimeters, then one Vernier division mathematically has to be 0.09 centimeters. To find that tiny visual gap we just talked about, we simply subtract the Vernier division from the main scale division. 0.1 minus 0.09, that leaves us with exactly 0.01 centimeters.
I want you to literally burn this standard least count number into your mind. 0.01 centimeters. This is your baseline. But, and this is a big but, you have to be prepared for tricky exam questions to completely alter this baseline just to test if you actually understand the underlying concept. Which brings us to Section 3, Zero Error Correction, Fixing Flaws. Let's talk about zero error. If you close the jaws entirely, and the Vernier 0 rests to the right of the main scale 0, your instrument has a positive zero error. Basically, it's adding a phantom length to every single thing you measure. So you've got to subtract this extra value from your final reading. On the flip side, if the Vernier 0 rests to the left, it has a negative zero error. You're starting below 0, which means you must add that missing length back to your final measurement to get the true, accurate value. Makes sense, right?
All right, Section 4, when formulas fail, the ultimate plot twist.
So what happens when an examiner decides to throw you a massive curveball and states that 10 Vernier divisions match 11 main scale divisions? Think about it. If you try to use your standard least count formula of 1 MSD minus 1 VSD here, it's literally going to output a negative number. The standard formula will completely fail you. The solution here is to rely on what we call visual math. You've got to picture the scales and treat the lengths as tangible physical segments. You literally measure the total distance on the main scale up to the coinciding point, let's just call it length x, and then you subtract the total distance on the Vernier scale, length y, to find the actual physical gap. Remember, it's geometry, not algebra.
Let's put this into practice with Section 5, IIT PYQs, the ultimate test.
Notice how simple a supposedly scary exam question becomes when you just organize the data. Take this 2021 JEE main question, for example. The setup reveals a standard caliper, but with a positive zero error of 0.02 centimeters. The main reading is 8.5 centimeters, and the sixth mark coincides. So, by taking that main reading of 8.5, adding our coinciding Vernier mark multiplied by our standard least count of 0.01, and then logically subtracting that positive phantom error we found, we easily secure a final precise measurement of 8.54 centimeters. Honestly, it's free points if your concepts are clear.
Now let's look at a significantly tougher scenario. This 2016 JEE Advanced question introduces Caliper 2. This is an abnormal scale where 10 Vernier divisions match 11 main divisions. Sound familiar? This is the exact trap we warned about earlier. It forces us to abandon the standard formula entirely and rely purely on our visual math.
The key here is figuring out the exact gap. By calculating the physical lengths of those 7 distinct segments on both scales and subtracting them, we find the actual physical gap, and then we just add it to our baseline of 2.8 centimeters. Just like that, we arrive at the correct reading of 2.83 centimeters without panicking.
Here's another fun way examiners try to trick you. In 2013, JEE Advanced threw a massive curveball with a completely non-standard main scale. This one is divided into 0.05 centimeter increments, and, get this, it utilizes 50 Vernier divisions instead of the usual 10.
But hey, we don't panic. By methodically calculating the new value of one Vernier division, which means dividing 2.45 by 50 to get 0.049, we easily determine the new least count is 0.001 centimeters. We plug that in, multiply it by the 24th coinciding mark, and boom, it leads us straight to the correct reading of 5.124 centimeters.
Now consider this older but highly relevant problem. This 2010 IIT JEE question is conceptually straightforward, but it strictly tests your calculation speed. Here, 20 Vernier divisions correspond to exactly 16 main scale divisions.
Finding the Vernier division value allows us to instantly calculate the least count. 1 millimeter minus 16 over 20 millimeters gives us a nice, clean least count of 0.2 millimeters. When you truly understand the instrument's anatomy, you can instantly secure those points.
Sometimes examiners brilliantly mix concepts, like attaching a Vernier caliper to a stretching wire. This specific question requires you to first use the physics of Young's modulus to discover that the wire actually stretched by an absolute length of 0.3 millimeters.
And here is where the conceptual magic actually happens. Since we know the standard least count is 0.1 millimeters, a physical stretch of 0.3 millimeters dictates that the Vernier scale shifted exactly 3 units down. Therefore, the third Vernier division must now perfectly coincide with the main scale. No heavy math required here, just pure visual logic.
So, the ultimate takeaway from all this is that once you learn to trust visual concepts and physical geometry over rote memorization, a whole new world of understanding opens up. You really have to wonder, what other notoriously tricky physics topics can you completely demystify by simply understanding the underlying logic? Keep questioning, keep visualizing, and I'll catch you in the next explainer.